The last section of our first of several equilibrium units is concerned with what happens after equilibrium is established. Once everything is kind of in its nice harmonious state where our rates of forward and reverse are equal, we have no net change of products or reactants happening over time, everything's staying the same. What happens when we disturb that equilibrium? And this essentially boils down to what is called the Chatelier's principle. And so, this is a French scientist in, terrible with years, 1800s maybe, looked at this idea of what happens when we mess with equilibrium. So that's the question we're answering here. And it is pretty convenient that the answer is going to come forth right now. Whenever we mess with an equilibrium, the equilibrium will do whatever it can to fix itself. So when an equilibrium is disturbed, the system adjusts accordingly to restore equilibrium. And we're going to have a couple ways of disturbing equilibrium. We can disturb it in various ways. We can disturb, let's try that again, disturb the concentrations. We can disturb the pressure. We can disturb the temperature. Or we can add or remove catalysts. These are all disruptions we can do. And if we consider concentration is N over V, right? That's moles per liter. P, pressure and temperature, we're again looking at all of our ideal gas quantities, right? So with reactions in equilibrium, we can mess with certain things. And we're going to look at each of these situations and see how the equilibrium will adjust when we mess with concentration, when we mess with pressure, when we mess with temperature. What happens to the equilibrium? And once we know what happens to the equilibrium, we can figure out how it's going to adjust. When we discuss this, we typically consider the following just generic equation. Reactants going to products. Typically, when we're talking about equilibrium adjustments, we talk about things where it says we shift left. That means we shift towards reactants. So if that means the reaction is going to go in reverse. So if we're going to favor the reactants, if we're going to start making more reactant, we call that a shift left. Or, on the other hand, if we're going to shift to make more products, we shift right. And we just use these terms left and right here, where left refers to the reactant side, and right refers to the product side. And so we can go through this in kind of an order here. What happens when we disturb concentrations? So, I know you've never seen this equation before, but here it comes. Oh my goodness, where did this equation come from? Wow. We saw in one of our previous sections how to use the reaction quotient Q. We saw that Q was a useful tool for imagining where a system was at a given point in time, and by relating Q to K, whether it was QC, KC, QP, KP, we would evaluate which way the equilibrium is going to go, right? And the same thing is going to happen here. So by messing with the concentrations, say we're going to add some NH3 to this system. It's already at equilibrium. Now we're going to add some ammonia. If we add ammonia, what's going to happen? That disrupts the equilibrium, right? Because now, at equilibrium, Q is the same as K, right? The reaction quotient and equilibrium constant are the same. But now that we've added NH3, So adding a product means that Q is now going to be greater than K, because remember, product over reactants. So increasing your products means Q is going to get bigger. If Q is bigger than K, that means we shift to the reactants, right? That means we shift left. The equilibrium will notice, aha, I have too many products. Time to break them down and make some reactants. So it's going to shift the equilibrium to the left to make more reactants. Same thing, if we were to add a reactant, if we added H2, so assuming the system is at equilibrium, if we add hydrogen, then Q becomes less than K because we're making the denominator bigger. And as a result, we shift right. If Q is less than K, remember, we're going to make more products. We're going to push the reaction forward. So this is not something new. We can add products or reactants. If we add products, we shift to reactants. If we add reactants, we shift to products, always restoring that balance, the equilibrium. The same is true if we remove things. If we take ammonia out of the system, then we're going to make more ammonia because now there's not enough ammonia. Or if we remove nitrogen, N2, we're going to make more nitrogen. So the reaction is going to shift to the left to make more nitrogen. So the opposite would be here. If we're adding a reactant or removing a product, Q gets less than K, we shift right. So if we remove a product, we're going to make more of that product. And that's an important driving force for a lot of biological reactions, as well as reactions we see in organic chemistry, is this idea that if we can remove a product, say we have a product that is a gas and we open our system, that gas goes away, we keep pushing the reaction to the right because we're now removing a product. And if we remove a product, that forces the equilibrium to keep going to the right, making more products. So it's a way we can force reactions to happen. Same thing here, adding a product or removing a reactant. If you remove a reactant, you end up with the same Q is greater than K, and then you shift left. So these two would have the same effect. These two have the same effect. So adding a reactant or removing a product shifts right. Removing a reactant or adding a product shifts left. Hopefully pretty self-explanatory there. Let's look at what's next, pressure. With pressure effects, we're going to take a look at what happens to the system, right? So consider our favorite reaction, which we will never stop exploring, it seems. When we're looking at pressure and how we disturb equilibrium, we have to consider what pressure change we're doing. If we increase the pressure, meaning we move it to a smaller container, we push down on it on a piston or something, if we're increasing the pressure by changing the volume, making the volume smaller, therefore pressure goes up, the system notices that as a disturbance. It does not like pressure changes. Because we saw, in this case, we're looking at C for all these things, right? QC and KC. Here, we're looking at QP and KP, right? If we end up increasing the pressure, the system will note we have too much pressure. So it's going to go ahead and remove pressure. If we increase the pressure, the system will try to decrease that. The system will try and counteract whatever we try to do. Because equilibrium is harmony, it's balance. We mess with the balance, the system says, I will fix that. I will adjust now to undo all the things you just did. So if we increase the pressure, that's what we're doing. The system says, okay, I've got to fix that. I'm going to remove the pressure. And how does it do that? How can it decrease the pressure? Well, remember that ideal gas law tells us that identity of the gas doesn't matter. Pressure and moles are proportional to each other, directly so. So that means that in order to decrease the pressure, we shift to the reaction side with fewer gas moles. And so this is 2 moles of gas. This is 4 moles of gas. So in order to make the pressure decrease, it's going to produce more products in this case, because the product side has fewer moles of gas. Gas is what makes the pressure, right? So if it wants to decrease the pressure, it's going to decrease the moles of gas by moving to the side that has less, has fewer moles of gas. So 4 moles on the left, 2 moles on the right. If we have increased the pressure, system says, no, I'm going to decrease the pressure. I'm going to turn some of these more gas molecules into fewer gas molecules. So it's going to move to the right in this case. Remember, this one depends on the stoichiometry of the reaction. We can't say left or right necessarily here. It will always move to, if it's trying to decrease the pressure, it will always move to the side with fewer, whichever side that is. In this case, that's the right side. By contrast, if we decrease the pressure, it'll do the opposite. It'll say, okay, I have too low pressure. How do I make more? Well, I make more gas moles. And so it's going to go to the side with more gas if it wants to increase the pressure. Finally, we can look at temperature. I guess not finally, because we have technically one more after that. If we look at temperature, remember way back last semester we talked about how exothermic and endothermic reactions can occur and how we might include heat as part of those chemical reactions. Remember, for an exothermic reaction, we have our reactants going to products plus heat. An exothermic reaction produces heat. An endothermic reaction is having heat as a reactant. And so if we want to think about what effect temperature has on equilibrium, we look at which side the heat happens to be on. If it's an exothermic reaction, meaning heat is a product, and we increase the temperature, meaning we're adding more heat to the system, we're adding a product. And if we go back to what we saw before, adding a product will lead us to shift left. Doesn't matter if that product is matter or energy. Either one works. So if we're adding a product, we now have too many products. Too many products means we need to break those products down, make reactants. So treat heat as a product or reactant, depending on if your reaction is exothermic or endothermic. So if we take an exothermic reaction, so delta H is negative. If we add temperature, if we make the temperature go up, then the reaction will shift away from the side with heat. It'll shift to the left. So we're going to end up making more reactants as a result. On the other hand, if we take an endothermic reaction with delta H is greater than 0, then, and if we increase the temp, then the system, the reaction, shifts right. We want to heat up our endothermic reactions to get them to go to the other side. So again, in either case, treat your heat as a reactant or product. For an exothermic reaction, heat is a product. For an endothermic reaction, heat is a reactant. And treat it just like any other reactant or product. If you add more product, you've got to make more reactants. If you add another reactant, you're going to make more products. Same thing if we take things away, right? Take away heat as a product, we're going to make more products. If we take away heat as a reactant, we make more reactants. Pretty straightforward. And so if we look at the last case with catalysts, I'll just tell you now, all catalysts do is change the rates, right? They make reactions happen faster. They also make reverse reactions happen faster. And since we know equilibrium is when rates are equal to each other, and since all we're doing is changing the pathway, we're going to still have forward reaction having the opposite activation energy and delta H as the reverse reaction. Nothing's changed there. The catalyst works both ways. Nothing happens with equilibrium. So, no change. If we throw a catalyst in to a system that is already at equilibrium, nothing changes. If we take away a catalyst from a system that is at equilibrium, nothing changes. So, easy enough. Easy one. Ignore it. Nothing happens. So, with this chapter, or rather this section, we've looked at what happens when we disturb equilibrium. In all cases, equilibrium, the system will work to fix whatever disturbance happened, whether the disturbance was concentration, pressure, temperature, or the addition or removal of a catalyst. In either case, the system will do what it can to undo all of our work to restore equilibrium again. And so that concludes our equilibrium unit. In our next kind of section, we're going to look at equilibrium in the context of acids and bases.